Welcome to Q Point. We start a course on analog circuits employing discrete components. The discrete electronic devices we use are diodes, bipolar junction transistors, MOSFETs, etc. These devices are fabricated using semiconductors. So it is logical to first discuss the physics of semiconductor devices. Our discussion will be brief and qualitative without going mathematically rigorous. We begin with the conduction mechanism in metals and extend the theory to semiconductors. Upon completion of this lecture, you will be able to define and understand the concept of drift velocity, mobility, current density, conductivity, resistivity, and Ohm's law. Let us start. We know in an atom, electrons are orbiting around a positively charged nucleus in various shells. Each shell corresponds to a certain energy. As the shell radius increases, the electron energy also increases. The outermost shell is called the valence shell, and the electrons in the outermost shell or valence shell are called valence electrons. It is the number of valence electrons that primarily decides the chemical activity of an element. A metallic conductor has 1, 2, or 3 valence electrons. These valence electrons will freely move through the interior of the conductor if an electric field is applied. Consider the following metal. Say, for example, first we will consider a monovalent metal, sodium, which has only 1 electron in the outermost shell. So in a chemical reaction, sodium will try to relinquish 1 electron to obtain a stable configuration. That is why the sodium atom is highly reactive. The atomic structure is 281 and number of valence electrons is 1. A two-dimensional structure of sodium atom is shown here. So each atom provides 1 free electron in the structure. See, there are 15 atoms schematically shown here. This diagram is only a schematic diagram. And there are 15 electrons shown here. The total positive charges is equal to total negative charges, so that the material is electrically neutral. So each atom contributes 1 free electron. If 1 electron in the valence shell is removed, the remaining structure is a positive ion with plus 1 charge. That is marked here. This is the positive ion. This is called the core of the atom. So core means the nucleus, which contains protons and neutrons, and all electrons except those in the valence shell. The core is immobile and is regularly placed in the crystal. Now consider magnesium. The electronic structure is 282. So it contains 2 electrons in the valence shell. So each atom provides 2 electrons and the core will have a plus 2 charge. So there will be total 30 electrons here for 15 atoms. In general, a metal has a periodic 3-dimensional structure consisting of tightly bound ions and a number of electrons that move about freely. This theory is known as the electron gas theory of a metal. Now consider a metallic bar of length L and cross-sectional area A. An electric field is maintained across the bar by applying a potential of V volts across the metallic bar. Electrons will be accelerated by the electric field. See, you can see that the electric field is from right to left. This is the direction of the electric field. Electrons will be accelerated by the field and will move from left side of the bar to the right side against the direction of the field. Or speaking in other words, electrons will be attracted by the positive terminal of the battery. So electrons will move from left side to the right side of the metal. In this motion, they will collide with the ions. After each collision, electron loses energy and changes direction. So it's its magnitude of its velocity and direction of its velocity changes after each collision. The velocity of an electron increases linearly with time between collisions and is on the average reduced to zero at each collision. So at a collision, the electron may become zero velocity. Between collisions, it will be accelerated by the electric field and it will move towards the right. So the electron takes a zigzag path as shown here. The path of the electron is not a straight line. It is a zigzag path because of these collisions. So the electron will undergo some impedance or some block from moving from left to right. That is the reason for the resistance of the material. So on the average, you can see that the electron will travel from left to right. The distance traveled is L. Suppose T is the time taken. You can say that there is an average velocity for the electron to travel from left to right. This average velocity is called the drift velocity, designated v drift. Drift velocity is proportional to the electric field. So you can write drift velocity is equal to a proportionality constant mu into E, the electric field, where mu is known as the mobility of the electron. It is measured in meter square per volt second, or practically in a small units, centimeter square per volt second. Let there be n electrons uniformly distributed in the conductor. The length of the conductor is L and the area of cross section is A. Under the influence of the electric field, let an electron travels L meters in t seconds. So you can calculate the velocity. The drift velocity is then v drift equal to distance traveled by time L by t meter per second. The current, because we have an electron moving from one side to the other side, there will be a current. The direction of the current is opposite to the direction of flow of electrons. The current is the total charge passing through an area per unit time. That's how we define current. So we can define current as I equal to charge of an electron into number of electrons per time. So I is equal to Q into N divided by T amperes, where Q is the charge of an electron. You can manipulate this equation like this: Q into N by T, and multiplying and dividing by L, you will get the expression as Qn by L into L by T, and you can combine L by T is the drift velocity. So you can write this as Q into N into the drift velocity divided by L amperes. This is the expression for current. Current is equal to Q into N into drift velocity divided by L amperes. The current density J is the current per unit area, that is measured in amperes per square meter. So if you divide the expression for current by the area of cross section, you will get the current density. So J is equal to I by A. We have an expression for I here, Q into N into V drift by L by A. So this is the expression for the current density. And now consider L is the length of the conductor and A is the area of cross section. So L into A is the volume of the conductor. N, capital N, is the number of electrons uniformly distributed through the material or through the metallic bar. So N divided by volume will be the concentration of electrons. Electron concentration, we designate it as small letter. N divided by La equal to small n is the number of electrons per unit volume, called the electron concentration. So substituting these values, L into A is the volume, N by La is N. If you substitute N by La is equal to N, we get the current density is equal to Q into N into the drift velocity amperes per square meter. This is the expression for current density. Again, we can write this as Qn into drift velocity is equal to mu into E. So you can write this as J is equal to Q into N into mu into E, or you can write J is equal to sigma into E, where sigma is the conductivity of the material. Sigma is equal to Q into N into mu. This is the conductivity of the material. Reciprocal of conductivity is the resistivity. And you can note an important point here, conductivity is proportional to electron concentration. The higher the electron concentration, the higher the conductivity, or the lesser the resistivity. So we have an important expression, J is equal to sigma E ampere per square meter. This is actually Ohm's law. We will see how this becomes Ohm's law. We have the electric field E is equal to voltage divided by length. V E is equal to V by L, or this implies V is equal to E into L. Now, using this expression in the expression for J, the current density Vt, we have current density, we have I is equal to J into A, which is equal to sigma E into A. J is equal to sigma E. Now we will be using these expressions. This can be sigma E into A into L by L, multiplying and dividing by L, and combine this E and L together. So we will get this is equal to sigma into A by L into V. So we have I is equal to a constant into V, or you can write this as I is equal to V by R, where R is equal to L by sigma A. This is known as the resistance of the conductor. 1 by conductivity is equal to the resistivity, or you can write R is equal to rho L by A, where rho is equal to 1 by sigma is the resistivity of the material. The results we have derived here are applicable to semiconductors also. We will see how we will apply these results to semiconductors. So we have seen that the conductivity is proportional to N, the concentration of electron. Concentration of electrons means the number of electrons per unit volume of the material. Semiconductor materials have conductivity between those of conductors and insulators. Now we turn to semiconductors in the next lecture. These are the references, and thank you.